Okay, in this section we're going to talk about evaluating logarithms using a calculator, and we're going to talk about a very important result called the change of base theorem. Now, so far we've talked about logarithms, all right, in base a. That was the base, all right, and remember that a has got to be a positive number and is not equal to 1. And so really there's really an infinite number of bases. And so we want to restrict ourselves to bases that we can evaluate. And if you look on your calculator, you'll see that we do have a button that says log. That's because this is called the common log. All right, and it's a base 10. And there are many models in real life, right, in real life that require the natural log, or the log in base 10. So the first thing we want to be able to do is to evaluate in base 10, and we're going to use our calculator. So let's look at our first example. Let's suppose we want to use a calculator, right, to find the value, right, and we'll do a few of them. Let's say values of, all right, part A, let's do the log in base 10 of 10,000. All right, now we don't really need a calculator to do this, because we know that this is in fact log in base 10 of 10,000 is in fact log in base 10 of 10 to the 4, which would be 4. But we can verify that, because you can look here that we have, we want to put in 10,000 and then hit log in base 10, and there it is, 4. Okay? Right, so let's do part B. All right, so don't forget the properties of logs. So let's suppose we want to look at log of 341. So again, this means log in base 10. So of course we end up with 341. We hit log in base 10, and we end up with 2.53. All right, and of course we can take it to as many decimal places as we like. So let's go 3, 2, 7, 5, 4, 4, for example. All right, it does go further, but I've rounded off to 7 decimal places. All right, let's do part C. Let's suppose I want to find the log of 0.06894. All right, so again, we come up here, we see that we have, let's cancel that one, we're going to have 0.06894, and we hit log in base 10. Notice it's a negative number, which makes sense, all right? And so we end up with this being negative 1.1615287 actually, if I round it off there. All right, so there we have a way of doing this using a calculator. Now we next want to talk about some applications, all right, of using the natural log. And the very first application comes from chemistry, right, which says this, that in chemistry the pH of a solution is defined as pH equals the negative log, notice this is base 10, of H3O plus, which is actually the hydronium ion concentration in moles per litre. Now, if you don't do chemistry, it doesn't matter. This is just a measurement of the number of moles per litre of this particular element. The pH value is a measure of the acidity and the alkalinity of a solution. And pure water has a pH of 7. So that's our sort of measuring point there, where that's neutral. And substances with pH values greater than 7 are what we call alkaline. So notice that goes to the blue section. And pH is less than 7 is acidic, and that's going towards the red. We use litmus paper to actually measure this. And the paper goes blue if it's alkaline and red if it's acid, and it just stays natural if it's got same as water. So it's customary to round pH values to the nearest tenth. Right, so let's have a look at do an example of this. Right, let's suppose that we want to find the pH, right, of a solution. Okay, with, and let's do this as part A. All right, with a solution with the following number of hydronium moles equal to 6.8 times 10 to the negative 8. Okay. All right, so what we're looking for here, notice that pH is given by negative the log of the number of hydronium ions, which in this case is going to be negative log, this is base 10, remember, of 6.8 times 10 to the negative 8. Now we can use our log rules here. This is going to be, well, there's a couple of things we can actually do here. All right, we can actually write this as the negative, and let's do this, the log of 6.8 plus the log of 10 to the negative 8. Okay, because this is the log rules, this is a product here. Notice that we are multiplying. So we can use our log rule, which turns it, or log property that turns it into an addition. So this is going to be negative the log of 6.8. Notice negative, and notice now the log in base 10 of 10 to the 8, of course, is negative 8. Okay, all right, because it's the exponent. All right, so this is going to be, now we can get our calculator. All right, and we can put in here 6.8 and take the natural, the common log, and we get 0.832. So we end up with negative 0.8325, and we're going to round it off to the nearest tenth in a minute. Negative of negative 8 is plus 8, so I've got a negative of that. So I'm going to change the sign, all right, of this one. So I've got the negative there, and I'm going to add 8. And notice I get 7.167, so to round to the nearest tenth will be 7.2. So this will be approximately 7.2. Okay, so that's the pH. So the pH is approximately 7.2. Okay, so that's how we do that. All right, next. All right, let's do part B. All right, in part B, let's suppose we want to find the hydronium concentration of a solution where the pH equal to 4.3. So remember our pH here is given by, okay, notice where here it is here, negative log, which is base 10, remember, of the hydronium concentration. Now this time we have the pH, so what we have is 4.3 is equal to negative log of the hydronium concentration. Okay, so really we're having to work backwards here now. Okay, so in this case here, of course, we're going to need to, well, this implies if I put the negative on the other side, this is going to be the log of the hydronium concentration. Now, how do we undo a log? Well, we take a power of 10. So if I take the power of 10 of the log of the hydronium concentration, and we take that, all right, 10 to the negative 4.3, then the 10 exponential of 10 undoes the log in base 10. So this implies that the hydronium concentration is actually equal to 10 to the negative 4.3. Okay. All right, so when we do that, of course, we're going to need to get our calculator. Okay, so here's our calculator here. So notice that we have y to the x here. So I'm going to put in 10, hit this one here, and put 4.3, but negative, and then hit equals. Now notice we get 0.00005. 5. So if I remove the decimal place, I'm going to get 1, 2, 3, 4, 5. So it's about 5, all right, times 10 to the 5. Okay, so that comes out to be, the hydronium concentration is approximately 5 times 10 to the minus 5. Okay, and that's how we do those kinds of problems. All right, the next one is that how do we use this? Well, in the resources, land resources, we have classifications of what's called wetlands. All right, and these can be classified into 3 different kinds: bogs, ferns, marshes, actually 4, swamps. Okay, so these are all based on the pH value. So a pH value between 6 and 7.5 indicates the wetland is a rich fend. All right, so that's this one here. Okay, a rich one. Right, when the pH is between 3 and 6, we have a poor fend. When the pH falls to 3 or less, the wetland is a bog. Okay. Now, suppose that the hydronium ion concentration of a sample of water from a wetland is 6.3 times 10 to the negative 5. How would this wetland be classified? Right. Well, we know that the pH, right, is given by negative the log in base 10 of the hydronium concentration. So in this case we have negative log of 6.3 times 10 to the negative 5, which is going to be negative log of, well, let's do a property of logs here, 6.3 plus log of 10 to the negative 5. Okay, so in this case it's negative log of 6.3 subtract, now the log in base 10 of 10 to the 5 is negative 5, right? So this is going to be, now we need our calculator now. All right, so we end up with 6.3 and we take the log, so it's going to be negative, so negative 0.7793. Okay, and we're going to add 5. Right, so we now add 5 and we end up with 4.2. All right, so if we look up here, 4.2, all right, fits in between 3 and 6. So this water sample, right, comes from a poor fen. Okay, all right, so that's how we and that's how we do that one. Alrighty, so all right, so that's the pH application. Now we'll look at the next one. Okay, the loudness of sounds is measured in decibels. All right, we first assign an intensity, which is I0, to a very faint sound, which we're going to call the threshold sound. In particular, if we have a sound that has intensity I, then the decibel rating D of this louder sound is actually given by the formula D is equal to the sound, that's the sound we're measuring, and this is the threshold sound. Alright, so notice here that we have D is equal to, this is the decibel rating, is equal to 10 times the log, log, so it's base 10 of the sound we're measuring over the threshold sound, so the ratio of those two. So let's suppose we want to find a decibel rating of a sound with intensity of 10,000 I0. Alright, so what we have here is, notice that D is equal to 10 log of I over I0. Okay, which in this case here we have I is, so this will be 10 log of I is 10,000 I0 over I0. Notice the I0's cancel. So this is going to be 10 by the log of 10,000. Now we know the log of 10,000, right, because 10,000 is 10 to the power of 4, so it's going to actually be 10 times then 4, which is 40 decibels. Okay. All right, so that's our decibel rating for a sound that has 10,000 times the intensity of that threshold sound.